So welcome to all of you in lecture 6, which is based on Zeroth Law of Thermodynamics. Before starting this chapter, we have to understand some important terms like what is temperature? Okay. So temperature is a thing by which we can sense that any body, how much it is hot or how much that is cool. Okay. So by this we can sense, okay, this body is like a freezing cool. Okay. Or we can say that by this temperature term, we can sense that, okay, this body is like a red hot. So you can say that it is a quality type measurement. Later on, we will discuss temperature measurement in terms of quantity. Okay. So we can understand and we can measure this temperature in terms of quality or in terms of quantity. So firstly, we are talking about quality wise temperature measurement. So suppose there are two blocks in which in first block ice is filled and in second box hot water is filled. Okay. So if you touch one by one these blocks, so when you touch this block, at that instance you sense that, okay, this is a very cool block, and when you touch this hot water block, you instantaneously sense that this hot water block is hot. So this is a this is a quality type temperature measurement. Okay. We cannot measure what is the exact temperature of this block. We just compare. Okay. This block is hotter in compared to this ice block. Okay. So this is a quality type temperature measurement. So if we define heat, suppose there are two blocks. Okay. This block A and this block is B. And here temperature is like that, TA is greater than TB. And if I connect these two blocks with a conducting rod, then what will happen? Due to this temperature difference, TA is greater than TB, that's why their temperature difference is existing in between of these two blocks. So due to this temperature difference, there is energy transformation is taken place. Okay. So due to temperature difference, energy transformation is taken place in between these two blocks is known as heat. Okay. So due to temperature difference, energy which is flowing from higher temperature block to lower temperature block is known as heat. Okay. So this is all about heat. But how much time this energy will flow from this block to this block? This is the another question. कितने समय तक ये एनर्जी ए ब्लॉक से बी ब्लॉक तक फ्लो करता ही रहेगी? Okay, so this energy, this heat is flowing from A body to B body till both bodies will get same temperature. Okay, till both bodies will get same temperature. So it will take some time after T time. Okay, since here TA is greater than TB, so as this energy is flowing from A body to B body, consistently TA will goes down. Okay, and after absorbing this heat, temperature of B will becomes higher. Okay, so after some time there will be a situation in which TA suppose will get temperature T after some time, and TB will get temperature T in a same time interval. So in that condition, both bodies having same temperature. So at that situation, there is no energy transformation will be taken place. Okay, so this is the situation of thermal equilibrium. This is the situation of thermal equilibrium. Okay, so thermal equilibrium is defined in which both bodies having same temperature. Okay, so that is about thermal equilibrium. So firstly I discuss about temperature, and after that I have told you about heat, and after that we have discussed regarding thermal equilibrium. Okay, so these are three important terms which plays a very important role to define the Zeroth law of thermodynamics. So now we move towards our slide. So this is our slide for lecture 6, lecture 6, Zeroth law of thermodynamics. So what is temperature? Temperature is defined as, we are familiar with temperature as a measurement of hotness or coldness. Okay. Based on our psychological sensation, we express the level of temperature quality wise, like freezing cold, cold warm, hot, and red hot. Now we move towards explanation of thermal equilibrium. So thermal equilibrium, in which when a body is brought into contact with another body that is at a different temperature, heat is transferred from the body at a higher temperature to one at lower temperature until both bodies attain the same temperature, as I have already discussed in previous example. So at that point the heat transfer stops and the two bodies are said to have reached thermal equilibrium. The equality of temperature is only requirement for thermal equilibrium. Okay, so that is the necessary condition for gaining thermal equilibrium, that both bodies have same temperature. So here it is an example of iron and copper block. In the first condition, iron having 150 degrees centigrade temperature and copper have 20 degrees centigrade temperature. So when these two bodies will lie in a contact, okay, so in that case heat is transferred from iron block to copper block, because iron having higher temperature. So heat is always flowing from higher temperature to lower temperature. So here heat is transferring from iron to copper. After some time, we will see that iron will get temperature 60 degrees centigrade and copper will get temperature same 60 degrees centigrade, because heat is transferring in this case from iron to copper block until both blocks will achieve same temperature. Okay, so this is the situation when iron and copper block both will achieve same temperature. That is called thermal equilibrium condition. Okay, so that's all about thermal equilibrium. Now we move towards Zeroth's law of thermodynamics. Okay, so see that what is Zeroth's law of thermodynamics? Suppose there are three bodies. This body A, this body B, and this body C. There are three bodies. Body A has temperature TA, B having temperature TB, and C having temperature TC. Okay. So if I consider these two bodies, A and C, okay, firstly I consider these two bodies A and C, and the statement is that body A is alive in a thermal equilibrium with body C. ठीक है, body A and C, both bodies are alive thermal equilibrium to each other. Okay, so in that case, that means what is TA is equal to TC. Okay, in second statement, body B is alive in thermal equilibrium with respect to body C. Okay, body B is alive in a thermal equilibrium with respect to body C. So what mean? That means TB is equal to TC. So if we combine these two statements, okay, body A is alive with thermal equilibrium with body C, and body B is alive with thermal equilibrium with body C. So if we combine these two statements, so we can say that if body A is alive thermal equilibrium with C and B is alive in thermal equilibrium with C, so these two bodies are also alive in thermal equilibrium with each other. Okay, so we can say if we combine these two statements that TA is equal to TP. इंडिविजुअली अगर बॉडी ए सी के साथ में थर्मल इक्विलिब्रियम में है, इंडिविजुअली बॉडी बी अगर सी के साथ में थर्मल इक्विलिब्रियम में है, तो ये दोनों बॉडीज भी क्या होंगी, आपस में थर्मल इक्विलिब्रियम में होंगी, यानी TA that must be lie in thermal equilibrium with body B. Okay, so this is the Zeroth law of thermodynamics. Okay, it is widely used for temperature measurement. Okay, so we again move towards our slide. Okay, yes. So what is Zeroth law of thermodynamics? If two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. It serves as a basic for the validity of temperature measurement. Okay, so this is the Zeroth law of thermodynamics. And now another important term is what is thermometric property. So in order to obtain a quantitative measurement of temperature. Okay, in a starting we have discussed that temperature can be measured in two ways. First one, that is quality wise, by touching, by sensing. Okay, and second one, by quantity wise. So for that reason we need a thermometric property. So what is thermometric property? See, in order to obtain a quantitative measure of temperature, a reference body is used, and a certain physical characteristics of this body which changes with temperature is selected. The changes in the selected characteristics may be taken as an indication of change in temperature. The selected characteristics is called the thermometric property. Okay, and what is thermometer? The reference body which is used in the determination of temperature is called thermometer. Okay, so we can understand this statement with an example. Okay, so if there is a block, okay, suppose this is a block which having any generalized temperature T. Okay, so here I express this temperature theta. Okay, so we want to calculate this theta temperature. Okay, so in that case we have to consider a property which is varying with respect to this temperature. Okay, suppose I am taking a system which is constant volume. Okay, which is at constant volume. So if we increase temperature of this system, so what will happen? If we increase temperature of this system, pressure is also increasing. Okay, so we can say that in this system pressure is a thermometric property because temperature is changing with respect to pressure. So we can define a function which is we can define the function of temperature in terms of pressure. Okay, so this thermometric property is different for different system. Okay, we will see different types of thermometer in which thermometric properties are different. It may be pressure, it may be volume, or any other thing. Okay, so if we want to express this term in a mathematical manner, so we can say that theta, that is the function of x, theta, here theta, that is the temperature. Okay, so theta, that is the function of x, is equal to something small a and capital X. Okay, here theta, that is temperature of that body, and X, that is thermometric property. Okay, it may be pressure, it may be volume, or any other thing, and small a, that is constant. That is constant. Since theta x is proportional to x, that's why we can if we remove this proportionality term, then we have to put a constant term, small a. Okay, so this is the mathematical expansion, because here we assume that mathematical expansion between temperature and thermometric property is linear. So that's why we can write this term theta x, that is directly proportional to x. And if we remove this proportionality sign, then we have to put a constant. And finally, we will get that theta x is equal to ax, where theta, that is the temperature, and a, that is the constant term, and x, that is thermometric property. Okay. So that's about thermometric property. And the system which is used for measurement of temperature, that is called thermometer. Okay. So this is about that. Now we discuss some methods which is used for temperature measurement. Okay. So what are the methods? Here, before discussing methods, we see there are different types of thermometer. Okay. Thermometer, which is a device which is used for measuring temperature. So the first one, that is constant volume gas thermometer. Okay. So if there is a constant volume, so what is varying with respect to temperature? That is pressure. Okay. So that's why here thermometric property is a pressure which is changing with respect to temperature. So if we measure this thermometric property, then we can calculate whatever the value of temperature of that system. Second one, that is constant pressure gas thermometer. If there is pressure is constant, there pressure is constant, so which property is changing with respect to temperature? That is volume. Okay. So in this case, thermometric property is volume. Next one, electric resistance thermometer. So in electric resistance thermometer, there is a property resistance which is changing with respect to temperature. So that's why thermometric property in this type of thermometer, that is resistance. In thermocouple, that is thermal EMF, and in mercury in glass thermometer, by which we can measure temperature, that is the length of mercury. Okay. You can see this type of thermometer in labs and rooms for measuring temperature. So you can see that we can measure different temperature values with respect to mercury column height. Okay. See in lab or any hospital cabin. Okay. In such type of buildings, lots of mercury glass thermometer are fixed on the walls of cabin. So by this you can measure temperature in terms of length of mercury column height. Okay. So these are different types of thermometer by which we can measure temperature. Okay. Now we move towards different measurement methods for temperature. Okay. So before of 1954, we use two fixed points for measuring temperature, unknown temperature. Okay. So these are fixed point. The first one, that is ice point, 0 degree centigrade of water. And the second one, that is steam point. So in which manner we are calculating temperature through this method? I'm trying to show you. In previous topic, we already discussed that we assume that temperature variation is a linear proportional to the thermometric property. So we can say that theta x is directly proportional to x, or theta x is equal to ax. Okay. So if in this problem, in this method, we are taking two reference points. So first reference point, it is x1. Suppose it is a freezing point of water. Okay, and correspondence, its temperature is theta x1. Okay, it is ice point. Okay, and steam point, that is x2, and temperature respect to this reference point, that is a steam point. Okay, so temperature, that is 100 degrees centigrade. Theta x1, that is equal to 0 degrees centigrade. Theta x2, that is equal to 100 degrees centigrade, because water steam point is 100 degrees centigrade at atmospheric pressure. Okay, so these are the conditions. So these are known terms. We know x1 value at 0 degrees centigrade. We know x2 value at 100 degrees centigrade, and these value will depends what is a x1 and what is x2. That will depend upon which type of thermometer you are using. Okay, it may be if you are using constant pressure thermometer, then x1 and x2 are v1 and v2. If you are using constant volume thermometer, then x1 and x2 are p1 and p2. Okay, so these are the expressions, and we want to calculate unknown temperature theta x. Okay, we want to calculate unknown temperature theta x at thermometric property x. We can measure this thermometric property on this unknown temperature. Okay, we can measure this pressure on this unknown temperature. So how we get this value theta x? Okay, see that. So if we define this term, okay, we consider ice point and we consider this unknown temperature term. Okay, so by first equation we can write that theta x1 is equal to ax, and theta x, this is the unknown temperature, small a x, this is x1, and steam point equation theta x2, that is equal to ax2. This is equation first, this is equation second, and this is equation third. Okay, we consider firstly equation first and second and divide equation first to equation second. So what we will get? Theta x1 upon theta x, that is equal to a cancel, x1 upon x, that is equation 4. We are getting this equation by equation first divided by equation second. Okay, like that we divide equation third with equation second. So what we get? Theta x2 upon theta x, that is equal to x2 upon x. This is equation 5. Okay, this is equation 5. So if we separate these two equations, equation 4 and equation 5, so what we will get? If we separate equation 4 minus equation 5, what we will get? See, that is theta x, that is the LCM. We separate these two terms, theta x same. So in above, theta x1 minus theta x2, that is equal to x1 minus x2 upon x. Okay, so in this equation our motto is that we have to find this theta x value. So final expression for theta x is that is theta x is equal to theta x1 minus theta x2 upon x1 minus x2 and multiply by इसको मैं जो थोड़ा सा ऑफ कर देता हूँ, multiply by x. Okay, so this is the final term by which we will get a known value of theta. Okay, by which we get a known value of theta. Okay, so this is the method before of 1954 which was used to measure the temperature, and here you clearly see that there are two reference points, that is x1 and x2, and corresponding values theta x1 and theta x2 we are using to measure this unknown temperature theta x. Okay, so that's all about this method. Now we move again towards our slide. Okay, so this is the final expansion theta x equal to theta x1 minus theta x2 upon x1 minus x2 multiplied by x, where theta x temperature to be measured at x thermometric property, theta x1 that is a standard system temperature at x1 thermometric property, and theta x2 that is standard system temperature at x2 thermometric property. But here some limitations of this method. What? The difficulty of achieving equilibrium between pure ice and air standard water. Actually, at 0 degrees centigrade, when ice is in melting process, so what will happen during melting process of ice, in the neighborhood of ice, pure water is adjusting. We want to maintain thermal equilibrium condition between ice and atmospheric condition, atmospheric air. But in a practical manner, situation is that ice is covered in its neighborhood with respect to pure water. So that's why the original equilibrium condition will not be created on this situation. So this is the practical problem for maintaining equilibrium condition at the freezing point of ice. Okay, and the second one, that is extreme sensitiveness of the steam point to the change in pressure. Okay, second one fixed point is steam point of water. Okay, and at higher temperature, that is 100 degrees centigrade, when water is in the state of converting steam, at that situation, pressure, constant pressure maintaining is too much difficult. So that's why extreme sensitiveness of a steam point are lying with respect to pressure. Okay, and if we want to maintain thermal equilibrium between the water and steam point, then we have to maintain constant pressure in throughout the process. But again, we can say that it is a very difficult in a practical manner to maintain all such type of condition which is favorable to maintain thermal equilibrium on these two fixed points. Okay, so these are the limitation of this method. Now we move towards next slide. Okay, so this is the second one method which is used for temperature measurement after 1954. Okay, so what is this method? Since 1954, only one fixed point has been in use, that is the tipple point of water. In previous method, we are using two fixed point, but in this case, we use only one fixed point, that is the tipple point of water. What is tipple point? Tipple point is a state at which ice, liquid water, and water coexisting in equilibrium. That is the tipple point of water. Okay, tipple point is the state in which all three stages coexist in equilibrium condition. Okay, so tipple point of water is 273.16 Kelvin. Okay, that is for Kelvin. So in which manner we calculate unknown temperature? Through this method, see that. In the previous method, we discussed that theta, that is the temperature, is a linearly depend with respect to thermometric property X. So if we take in fixed point, that is the tipple point of water, so in that case, we represent temperature at tipple point, that is theta T, that is equal to 273.16 Kelvin. Okay, and that is equal to A, that is constant term, and xt. Xt, that is the thermometric property. It may be a pressure or it may be volume, whatever be. Okay, so this is the known condition for this method at tipple point. At tipple point of water. Okay, and now since it is known and it is known, so we can calculate small a value with respect to tipple point property and temperature. Okay, so what is a value? That is theta T and xt. These two terms known. Okay, so we can easily calculate value of constant term. Now the unknown temperature theta we have to measure. So for that, theta is equal to Ax. X, that is the thermometric property corresponding to this unknown temperature. Okay, so X is known. Okay, X is known. We have to measure this theta, that is unknown. So we put this A value by this equation, theta T upon xt multiplied by X. Okay, this is the equation. Now we know that theta T, that is the tipple point of water, is equal to 273.16. So if we put this value, then equation is that theta is equal to 273.16 upon xt, that is the thermometric property at tipple point, multiplied by X. X, that is the property, thermometric property at unknown temperature. So this is the final expression. By this we can calculate theta value, that is unknown temperature value, through second method which is used after 1954. Okay, so now again we move towards our slide. So this is the final expression, theta equals to 273.16 x upon xt, where theta, temperature to be measured at X thermometric property, and xt, that is thermometric property at tipple point temperature. The temperature of the tipple point of water, which is and easily reproducible state is now the standard fixed point of thermometry, because we by this method we can overcome through the limitation of first method. Okay, in first method we have to face lots of problems to maintain thermal equilibrium condition on fixed points. So nowadays we use this method in which we have to maintain single thermal equilibrium condition on a single fixed point. Okay, that is the triple point. So this is the second method. So in second method, जो एक्सपेंशन हम लोगों ने कैलकुलेट किया है, so for different types of thermometer, what is the second method expression we can see by this table. If we are talking about constant volume gas thermometer, so in constant volume gas thermometer, what is thermometric property? Volume is constant, so pressure is changing with respect to temperature. So in that case, final expansion of second method, that is 273.16 x upon xt. So here x, that is pressure. So pressure, that is the P, that is pressure at a known temperature, and PT, that is the critical pressure of that substance. Okay, so final expression is that theta equals to 273.16 P upon PT. For constant pressure gas thermometer, in this pressure is a constant, so volume is thermometric property, so theta equals to 273.16 V upon VT. An electric resistance thermometer, here R, resistance, is a thermometric property, so expression is 273.16 R upon RT. For thermocouple, that is EMF, is thermometric property, so theta equals to 273.16 E upon ET. And liquid and glass thermometer, that is in that case length is the thermometric property, so we can write second method expansion, that is theta equals to 273.16 L upon LT. Okay, so these are the different expression for different types of thermometer. Now we discuss this problem for, to understand the concept, in which manner we apply this theory to calculate numerical problem. Okay, so what is problem? Problem is that the limiting value of the ratio of pressure of the gas at the steam point and at the triple point of water when the gas is capped at constant volume is found to be 1.36605. What is the ideal gas temperature of the steam point? Okay, so this is the question. So firstly I write this problem. See, in question, the limiting value of the ratio of pressure of the gas at steam point and at the triple point of water when the gas is capped at constant volume is found to be 1.36605. Note down this point that in this problem we are using constant volume type gas thermometer. Okay, so if we are using constant volume type gas thermometer, then in that case there is a thermometric property which is pressure. Okay, so that's why in this problem this is given that pressure of gas, ratio of pressure of gas at steam point and triple point of water. Okay, so this is the expression P upon PT. P upon PT, that is pressure at steam point upon pressure at trickle point, that is equal to 1.36605. 6605. This is given. Okay, this ratio is given. And what is the ideal gas temperature of steam point? We have to calculate this theta corresponding to this pressure P. Okay, we want to calculate this theta corresponding to this pressure P. So what is the expression of second method for constant volume gas thermometer? That is theta equals to 273.16, that is multiplied by P upon PT. Okay, so we can put this value 273.16 P upon PT, that is given 1.36605. So when you calculate this term, this is approximate 373 point, I think 16. Okay, this is the term. So since you are using this 273.16, that is the triple point of water in Kelvin scale. Remember this. You are using triple point of water in the expansion 273.16, that is in Kelvin scale. So that's why you will get this unknown temperature theta. It is also in Kelvin scale. So if you calculate this theta in degree centigrade, then you will get 100 degrees centigrade, because there is a relation between Kelvin scale and Celsius scale is that is C equals to K minus 273.16. Okay, 273.15 होता है. ठीक, this is the conversion expression. C equals to K minus 273.15. So this is the, I think, 15 Kelvin. Check this. Check this. By product, you will get final expression, and the final answer, that is goes to 100 degrees centigrade. Okay. So this is the problem which is based on the second method. After that, in next lecture, we discuss different types of thermometer and other methods which are using to measurement of temperature of different types of blocks. Okay, so we will discuss these all in upcoming lecture. Okay, thank you very much.